Hi, I'm Roland van Roy. In a previous tutorial video, I showed you how to make this DC-DC buck converter prototype and quickly check the converter stability by measuring the step load response. In this tutorial video, I will show you how to measure the converter loop gain and phase, which will tell you more about the converter stability. For the test equipment, I will use the PicoScope in combination with a frequency response analyzer add-on utility. I will also show you how to make this signal injection transformer which you need for the measurement.
In this example, we will check the stability of a current mode buck converter, which consists of a power stage with inductor and output capacitor and the load. In a current mode buck converter, the internal clock determines the switching frequency and activates the high-side MOSFET. The current in the high-side MOSFET is sensed and fed back with some slope compensation to a comparator. A portion of the output voltage is fed back to an error amplifier, which compares the feedback signal with a fixed reference voltage and adjusts its output accordingly. The output of the error amplifier is compared with a current sense ramp, and the high-side MOSFET is switched off when the current ramp exceeds the error amplifier voltage. When the output voltage drops due to a load increase, the error amplifier output will increase. This means that the current needs to ramp higher, so the duty cycle will temporarily increase, thereby increasing the output voltage to regulate the output back to its target value. The control loop consists of the modulator plus power stage and the feedback network, error amplifier and compensation. The modulator power stage has a dominant low-frequency load pole and a sample and hold high-frequency double pole. When using ceramic output capacitors, the output capacitor ESR0 will lie at relatively high frequency, often above the switching frequency, so you won't see it in this gain and phase graph. The error amplifier inverts the feedback signal and provides high loop gain at low frequency to achieve good voltage regulation. The C-comp capacitor forms an integrator at low frequency, resulting in dropping gain. A zero formed by C-comp and R-comp sets the mid-frequency gain and provides a phase boost. The compensation parallel capacitor then forms a high-frequency pole to make the system less sensitive to high-frequency noise. The sum of the modulator and compensator gain and phase gives the total loop gain and phase. The loop gain gradually drops, and the point where it crosses 0 dB is called the unity gain frequency or crossover frequency. The total phase shift of the loop should never reach 360 degrees at this frequency, because it would create positive feedback and make the system oscillate. A robust design needs a certain phase margin with respect to the oscillation point. In most current mode buck converters, we set the unity gain frequency around 1/10 of the switching frequency, which is a good compromise between converter speed and stability. This is done by adjusting the compensator mid-frequency gain. Lower compensation gain reduces the unity gain frequency. For most designs, at least 45 degrees of phase margin is needed. You can also look at the slope of the gain curve where it crosses the 0 dB line, which should be 20 dB per decade for good stability. When you set the compensator 0 frequency to coincide with the modulator load pole frequency, the loop gain drops at a steady 20 dB per decade and the phase is relatively flat. The converter loop gain and phase can be measured by injecting a small sine wave signal into the loop and measuring the converter output signal versus the input signal. The amplitude ratio of the output versus the input is the loop gain, and the phase difference between the output and the input is the loop phase delay. In practice, we use a network analyzer or frequency response analyzer with a tracking generator. A small resistor is inserted in the loop and the sine wave signal is applied across this resistor via a transformer to provide isolation between the equipment and the device under test. The insertion point should have a low output impedance and high input impedance. The sine wave frequency is swept and the input and output signals are measured over the sweep frequency. The loop gain and phase are calculated and shown versus frequency as a Bode plot. Gain phase measurements are often performed using network analyzers or frequency response analyzers. Drawback of these devices is that they only show the result in the frequency domain. For this video, I will use a PicoScope and a frequency response analyzer utility. The advantage of this equipment is that it lets you look at the signals both in time domain and in frequency domain, which gives you a better understanding of the measurement and can be used to check the converter operation during the gain phase measurement. PicoScopes are PC oscilloscopes. The hardware is connected to your PC, which runs the PicoScope software. For the gain phase measurement, the scope channel A is connected to the loop input and channel B is connected to the converter output. PicoScopes have a built-in generator, which is used for the injection signal, so the generator output is connected to the signal injection transformer input. You can use another channel to measure the converter switching signal to check the converter operation at different injection signal frequencies and amplitudes. In this video, I'm using a PicoScope 5444B, which has high resolution and low noise floor, which is beneficial for gain phase measurements, but you can also use the lower end PicoScopes. The PicoScope Frequency Response Analyzer utility was developed by Aaron Hexamer, who is a member of the PicoScope online community. He graciously shared his work for free. Please see the description below this video for the download link. After installing the utility, it will search for a connected PicoScope and you will see the main menu. You can select the input and output channels and probe attenuation. Since the measured signals are quite small, it is best to use one-to-one probes and settings. The stimulus sets the generator sine wave amplitude during the measurement. Here you can set the start and stop frequencies. Note that low frequency measurements take more time than high frequency measurements. In the Tools Settings menu, you can choose the more advanced settings. I will mention the most important ones. For gain phase measurements in switch mode power supplies, you should always choose the noise reject mode. Minimum cycles captured can be kept around 16, but keep in mind that a 1 Hz stimulus measurement would take at least 16 seconds. Lower noise reject bandwidth will improve the signal-noise ratio but requires more samples. A good value is the minimum measurement frequency divided by the number of captured cycles. The noise reject time base must be set low enough to get a sample rate that is at least double the converter switching frequency. The Axis Setting menu lets you set the plot scale and grid. I recommend using symmetrical scales for gain and phase, so the 0 dB and 0 degrees line up. Let me first show you how to make the signal injection transformer. To make a transformer that can achieve a flat response over a wide frequency range, you need to have a high primary inductance and very good winding coupling to minimize the leakage inductance. You can use the core of a high current common mode choke. In this case, I use the core of a Coilcraft CMT4 10 mH toroid common mode choke. First, remove the plastic and the wires. For the windings, I used a twisted pair from a Cat5 Ethernet cable. For this transformer, I needed around 7.5 meters of wire. Start in the middle of the wire and start winding one end to fill the complete core. Place the windings tight. Then start the other wire end and wind the second layer, finishing close to the previously finished winding end. Now separate the twisted wire ends and then twist the wires with the same color to form the primary and secondary winding. Let's use the PicoScope with a sine wave generator to look at the transformer input and output signals. Connect the PicoScope generator to the transformer input, connect channel A to the transformer input and channel B to the transformer output, and terminate the transformer with 10 ohms. I have set the generator at 10 kHz and 1 volt peak. The top blue waveform is the input signal and the red bottom is the output signal. If the signals are out of phase, just reverse the probe connection at the transformer output. You can see there is some attenuation from the transformer input to output. This is caused by the transformer wire resistance, which is around 2 ohms. When we increase the frequency, you can see that the output voltage starts to drop above 100 kHz, while the input voltage increases. This is due to the increasing impedance of the leakage inductance, which forms a low-pass filter with the termination resistance. Let's look at the low frequency range. When going lower than 5 Hz, you can see some distortion in the waveform. This is caused by transformer core saturation. At low frequency, the magnetization current in the primary increases, and the high mu core saturates. To measure accurately at low frequencies, you should reduce the signal generator amplitude. A 100 mV peak generator setting will not cause saturation at low frequency. You can also use the PicoScope FRA utility to measure the transformer input to output transfer. We sweep from 1 Hz to 1 MHz. To avoid saturation, set the stimulus at 200 mV peak, which is the same as 100 mV peak. For this measurement, you don't need noise reject mode, and I set minimum cycles captured at 4 to speed up the low frequency measurement. You can see from the result that the response is quite flat from 3 Hz to 100 kHz, which is good enough for gain phase measurements on most converters. If you need flatter response in the high frequency range, you can reduce the number of windings, which lowers the leakage inductance. Note that you don't see the attenuation caused by the 50 ohm generator impedance in the FRA result, because the blue reference signal is connected after the 50 ohm generator impedance. Let's measure the loop gain and phase of the RT7257G 800 kHz 5 volt 2 amp buck converter prototype that I introduced in the previous video, where I used Richtek's designer to generate the schematics and showed you how to adjust the compensation gain with respect to the effective output capacitance, basically to keep the crossover frequency around 1/10 of the switching frequency. You can also see that the tool has set the compensation zero frequency to coincide with the converter load pole. Note that the IC internally has 11 picofarad capacitance from comp to ground, which gives a high frequency pole at 880 kHz. The simulation AC analysis shows good stability. The crossover frequency is at 83 kHz and the phase margin is 62 degrees. You can see that the gain shows a steady 20 dB per decade drop. The phase starts to drop quickly above 100 kHz, and the gain margin, where the phase crosses 0 degrees, is 16 dB. To verify these results via real gain phase measurements, we need to insert the small 10 ohm resistor in the feedback loop of the self-made prototype board. It is best to place this resistor close to the output capacitors, away from the inductor, to minimize noise pickup from stray magnetic field. Then connect the transformer output to this resistor and measure the loop input and converter output signals with the PicoScope. Let's first check the loop input and output signals in the time domain via the PicoScope in scope mode. For this measurement, it is best to ground the PicoScope to your working table earth connection. I have set the probes at 1:1. Please keep in mind that the scope inputs can handle up to 20 volts. I set channels A and B at 20 MHz bandwidth limit. Don't connect the probes with long ground wires directly to the measurement points. The inductor stray field will couple noise into the probe loops. It is better to bring the measurement points and ground away from the inductor via 3 wires twisted together and connect the probes here, which reduces noise pickup. I apply a 5 ohm load to the converter for a 1 amp load current. This will keep the converter in continuous conduction mode, which is the operation mode we want to check for stability. I set the generator at 1 kHz and 500 mV peak, which gives a transformer output signal of around 90 mV peak. Before we switch on the converter, the output signal is basically grounded for AC signals due to the converter output capacitors, so you only see the loop input signal. When we switch on the converter, you now see that the converter generates an output signal which basically cancels the injection signal, so the loop input signal is almost gone. At 1 kHz, the loop gain is very high, so the ratio V out over V in is very large. It's also a good idea to look at the converter switching signal to see the effect of the injection signal on the converter duty cycle. Note that when you connect channel C probe directly to the switching signal, channels A and B show more noise. This is caused by the capacitive current in the channel C probe, which induces ground noise and influences the other channels. It is better to measure the switching signal by capacitive pickup. Place the isolated probe tip close to the switching node. Now you can see the switching signal without inducing noise in the other 2 channels. When you trigger on the switching signal, you can see that at 1 kHz injection signal, the converter duty cycle hardly needs to change to generate the 90 mV peak output signal. Let's increase the injection signal frequency. You can now see that the converter input signal slowly increases, which means that the loop gain reduces. Above 30 kHz, you can also see that the switching signal duty cycle varies more. This is caused by the attenuation of the Buck LC filter above its resonance frequency. At higher injection frequencies, the converter will need to increase the duty cycle swing to generate the sine wave output signal. At 200 kHz injection frequency, you can now see that the switching signal duty cycle shows extreme fluctuations, hitting minimum and maximum duty cycle limits, and at some points the converter even goes into discontinuous mode. For accurate gain phase measurement results, the converter operation must stay within its linear operation range over the entire sweep frequency range, and should not switch from one operation mode to another. To accomplish this, reduce the injection signal amplitude to keep the worst-case duty cycle variation at moderate levels. By showing the switching frequency in persistence mode and sweeping the generator frequency from 10 kHz to 200 kHz, you can easily check the duty cycle variation. In this case, 100 mV peak injection amplitude keeps the converter duty cycle variation within acceptable limits. You can see that the input and output sine waves have equal amplitudes around 80 kHz injection signal frequency. It means that the converter unity gain frequency lies around this frequency. We can now use the FRA utility to measure the converter loop gain and phase accurately. I set the injection signal at 200 mV peak, sweep from 100 Hz to 1 MHz with 100 steps per decade. In advanced settings, I chose noise reject mode, minimum cycles captured at 16, noise reject bandwidth at 6 Hz, and noise reject time base at 52 for 2.5 MHz noise reject sample rate to avoid aliasing with the 800 kHz converter switching frequency. I set symmetrical vertical scales with similar values as the simulation result. The plot shows that the gain indeed drops at a steady 20 dB per decade up to the crossover point. At low frequency, the plot shows some noise. This is due to the very small input signal amplitude in the high gain region. In the high frequency area, the phase drops very fast and wraps around the plot. You can unwrap the phase if you want. Check the phase margin and gain margin boxes to show the values in the plot. Use the mouse to zoom in. The crossover frequency is 78 kHz, the phase margin is 52 degrees, and the gain margin is 13 dB. The simulated values showed slightly higher phase margin, 62 degrees. This difference is probably caused by tolerances or model inaccuracies. Just to show you what will happen when you use too large stimulus amplitude, we set the stimulus at 1 volt peak-peak. You now see that the curves show irregularities in the mid and high frequency area caused by converter nonlinear behavior. You also see lower crossover frequency and higher phase margin. It is best to always check the signals in the time domain before running the FRA. You would expect that at higher load, the load pole will shift to a higher frequency and result in higher crossover frequency. But this is not the case, because higher load will also reduce the modulator gain and the crossover frequency will remain unchanged. An actual measurement at higher load shows a lower crossover frequency and better phase margin. This is caused by temperature drift of IC internal parameters due to the higher silicon die temperature at higher load. Note that at very light load, the RT7257G will automatically enter discontinuous pulse skipping mode. In this mode, the error amplifier is bypassed and the IC regulates on the output voltage ripple valley. Gain phase measurements in this pulse skipping mode can give strange results and are not really meaningful. Let's have a look at a marginal stability case. I increase the compensation gain by increasing the R-comp value from 15K to 33K. This will push the crossover frequency to a higher value into the region where the phase has dropped quickly. It will result in very low phase margin. Before we run the FRA, let's quickly double-check the signals in the time domain. We sweep with 100 mV peak generator amplitude in persistence mode. You can see that the duty cycle in the high frequency range shows a much larger deviation than before. Due to the lower phase margin, the converter will now show a tendency to oscillate around the crossover frequency. This results in peaking of the stimulus signal around this frequency and leads to a larger duty cycle variation. For accurate results, we need to reduce the stimulus more to keep the duty cycle variation moderate. In this case, I reduced the stimulus to around 30 mV peak. We can now run the FRA and set the stimulus at 60 mV peak, which is the same as 30 mV peak. The FRA clearly shows a higher crossover frequency and worse phase margin, 115 kHz and 26 degrees. This is not a good design, and you should reduce the compensation gain to reduce the crossover frequency and get better phase margin. I recommend checking the converter load step response as well. Here I'm using the Richtek fast load transient tool to apply a 1 amp static load and a fast 1 amp load step by selecting the 4.7 ohm dynamic load resistor. I measure the converter load current and the output voltage response. You can see that the step load response shows severe ringing, which is a clear sign of insufficient stability. The ringing frequency will normally be slightly higher than the converter crossover frequency. In this case, I measured 138 kHz ringing frequency.